Alright guys, so today we're going to be talking about Bezier curves. This is just going to be probably the first video of a mini series on spline geometry, just because I think it's very useful. And it's pretty cool stuff. So anyway, let's talk about what a Bezier curve is. I'm sure most of you guys back in preschool, you might have done something like this. Maybe not preschool, maybe like an art class. Anyway, if you wanted to draw a smooth line between something, what you would end up doing is you do a bunch of like this kind of stuff, you know? Yeah, and then what you would do is you connect the dots or connect the intersections, you know, and you'd have a nice smooth curve. So this is the same idea behind the Bezier curve. So we're going to investigate this a little more. So what we want to do is we want to describe those Bezier curves mathematically so that we can actually use them. Let's do this. Let's say I have a point, I'll call it P0. I have another point, P1, and I have yet another point, P2. Let's just use the case of 3 points right now. So from these points, I get this what's called a control polygon. Basically what this means is that my curve is going to exist within this control polygon. Now to construct the actual curve, what we do is we just interpolate along each leg of this control polygon. So I'm going to define a new point. I'm going to call it, I'll just draw it right here. I'm going to call it Q0. And I'm going to draw it right here again, Q1. And then what we have is yet another line that connects Q0 and Q1, and on this line is going to be another point that I will call C, and this is the point that's going to define our curve because there's no other series or layers of interpolations that can be done because it's only one point, only one leg. So what's going to happen is this Q0 and Q1 are going to interpolate along the blue dashed lines, and simultaneously this C point, this green point right here, is going to interpolate along the green dashed line. So first let's go ahead and define a parametric variable called t, and t is going to range from 0 to 1, and we'll see why in a little bit. So let's go ahead and write an expression for the position of point Q0 as a function of t. So first of all, let's go ahead and break down this linear interpolation. Whenever t is 0, we want our point Q0 to be at P0. So it's going to start at P0, and it's going to linearly increase its distance from P0 all the way to P1. So by the time we get to t is equal to 1, we're going to be all the way far away from P0, so whatever is multiplying by P0 is going to be 0, and instead we're going to be ramping up all the way towards P1. So we can actually write that as P0 times 1 minus t, which is this ramp down function, plus the ramping up function, which is P1 times t. So that is the position of Q0, and we can do the same thing with Q1. We just have to replace these subscripts. So instead we get P1 times 1 minus t plus P2 times t. So again, these two equations describe the movement or the interpolation of a point Q0 all the way to from P0 to P1, and Q1 from P1 to P2. And it's going to interpolate linearly, so it's going to remain at a constant speed as a function, or as t increases. Okay, so that's the first layer of interpolations. Now we also have this interpolation, and again, this is just the same thing. We can say C is equal to, again, a linear interpolation, but instead of dealing with P's, we're dealing with Q's now. Let's forget about the movement of Q, and what we can write this as is just like we did above. It starts at, whoops, that was a terrible Q. It starts at Q0 times 1 minus t plus Q1 times t. And now since we have expressions for Q0 and Q1, since they are moving, they are also functions of t, let's go ahead and substitute in for them. So we have C is equal to P0 times 1 minus t plus P1 times t, and all that, which is Q0 times 1 minus t, and then plus Q1, which is P1 times 1 minus t plus P2 times t, all that times, just a t. So let's go ahead and simplify this a little bit. So we get, I'm going to write it out here, so C is equal to P0 times 1 minus t squared plus P1 times t times 1 minus t, and again another P1 plus P1 times t times 1 minus t from that second term, and then finally plus a P2 t squared. Let's go ahead and simplify that one last time. We get P0 times 1 minus t squared, and then plus a P1 times 2t times 1 minus t, and plus a P2 t squared. So what we just derived here are actually called the basis functions. This, and this. These functions of t, these are actually referred to as the basis functions for a quadratic Bezier curve. It's a quadratic Bezier curve because there were 2 layers of interpolations. And that's why we have this degree of 2 on our polynomials. So we're going to call this one b1, this one b2, and this one b3. And the way that we typically express spline curves is a summation of the basis functions weighted by the control points. So what I mean by is this. All you do is add up the control points times the basis functions. In this case, it's going to be P0, B0 plus P1, B1 plus P2, B2. And I just realized that this should be, I started from a 0 index, so let me just change these right here. Okay. So this is how we express our curve, and what's cool about working directly with this basis, these B0, B1, B2 functions, is that you can create these smooth, nice curves simply by manipulating these control points. So if I move this control point, I will have a new control polygon now, and all that will happen is the curve changes. It still remains smooth. It still looks like a curve. It's just manipulated partially. So I know it's kind of hard to tell what I mean when I'm just drawing still pictures. So let's go ahead and take a look at what it looks like in MATLAB. Okay, so let's do a little bit of coding real quick. So first I'm going to define my parametric domain. Again, it's just t. It ranges from 0 to 1 like we established before. Next, I'm going to define my basis function. So we had b0, that was equal to 1 minus t squared. b1 was 2 times t times 1 minus t. And then finally, we have our third basis function, which was just a t squared. So the first thing let's do is let's just take a look at what this looks like in parametric space. So I'm going to plot b0, b1, and b2. Okay, so let's see what that looks like. All right, so this is what it looks like. We have our basis functions b0, b1, and then b2. So yeah, we can see that these are just quadratic polynomials. And what's interesting about this, let me just show you guys a little property of Bezier curves. So let's define a sum, b0 plus b1 plus b2, and let's just plot it real quick. Okay, so we can see this, that all across the parametric domain, when we add up the basis functions, they actually equal 1. So what this means is they partition unity. That's a unique property of splines. So if I were to take these, add them all up, I would get just a straight line at 1, just like we showed. All right, so anyway, let's continue on with this demonstration. Now let's define some points. We have P naught. Let's just pick a random point. Okay, now we actually need to define our curve. So we're no longer plotting in parametric space. We are plotting in physical space. And whenever we multiply a point which has different, different coordinates, an x-coordinate, y-coordinate, z-coordinate, whenever we multiply those by the basis functions, technically what we have is each basis function is being multiplied by the x-coordinate and then y and then z separately. So first let's define the x-coordinate of our curve, and that's just going to be the x-coordinate of our first point times b1 plus the x-coordinate of our second point times b2, and then plus, oh sorry, I did that again. This should be 1. We start at 0. B naught. Okay. And we're going to take that statement. Okay, so we have the x-coordinates of our points times our basis functions. Good. Now we're going to do the same thing for the y and z components, or coordinates, or whatever. But instead of the x-coordinate, we're going to take the y and z coordinates respectively, like this. And they're always multiplying by the same basis function. Okay, so now we can plot our curve. So c is really, we can express that as, x of t, comma y of t, z of t, like that, where this is x of t, that's y of t, z of t. So I'm just going to plot it like x, y, z, like that. I think I have to use plot 3, okay. Open up a new figure, actually. Okay, so let's see what that looks like. Oh, actually I'm also going to plot the control points as well. Alright, so this is what our curve looks like. So this is a three-dimensional curve. You can kind of see how these control points pull the curve towards it. So it starts at, so here you have the P naught and P2, and this P1 pulls the curve towards it. And again, this can work in, this generalizes to n dimensions, really. I can do this in 2D or whatever. But let's go ahead and take a look at how this control point affects it. So I'm going to change the coordinates of this guy right here, this P1, and I'm going to move it to the origin. So let's see what happens. So P1, I'm going to move it towards origin, and this is what we get. So I just moved it to the origin, and that happened. So it moved the curve a little bit. And you can kind of see that it's being pulled more towards the origin now. Let's move it up. Let's move it to let's move it to like 1, 1, 1. 1, 1, 1. Now changing P naught and P2 isn't going to do anything because it's interpolatory at the ends. Those are the start and end points. Okay, so yeah. So I pulled it to 1, 1, 1. It's pretty much like a straight line now. But you can still see how everything curves towards it. But what's cool about these Bezier curves, it gives you nice, smooth lines, which is desirable in a lot of applications, especially in some applications of analysis. All right, so back to the notebook paper. Okay, so let's go over what we just saw. So I said that we can express a Bezier curve or a spline curve in general as a summation of the basis functions multiplied or weighted by their respective control point. So each control point has a basis function associated with it. I can have as many control points as I want, but in the case of a Bezier curve, the more control points you add, the more layers of interpolation that you're going to have, and therefore the higher degree the polynomial. And generally, this actually is not desirable, because if you want to gain greater control of your curve and manipulate it and, you know, all over the place or whatever, however you want, it's going to raise the order of the curve, and you might lose some of the behavior that you want to capture. And that's where something called b-splines come in, but we'll get into that. We'll get to that in a later video. But anyway, let me just kind of show you again what's going to happen here. So these blue dots, those are your control points. Then along these, you have your first layer of interpolations. I'll draw it slightly offsetted. Okay. And then again, on top of this, since we're not down to only one leg, we're going to have another layer. So we have another layer that exists on the red lines, and they're going to interpolate along the red lines like that. We have one final layer of interpolations. Well, actually, never mind. We have two more. We have one right there along the green that connect the green lines, and then finally we have our curve. See this black line. So you can picture this thing just morphing, and as every point moves to the next point. So this red point is going to move from this guy to this guy right here. Yeah, so every point is going to move from one end of its line to the other end, and eventually what you have is this curve will probably look something like this. I don't know, it'll look something like that, but more smooth than that, obviously. So if that's hard to picture, let's take a look at Wikipedia real quick. Okay, so here's some pretty cool animations that I've just pulled up on Wikipedia. So you can see what I mean, how, let's take a look at this first one. This is pretty much the example that we worked out. You see these green points interpolating from P0 to P1, and then this guy on this side interpolating from P1 to P0, and at the same time the black dot, the curve, is interpolating along the green line, and you get this nice smooth curve that is basically controlled by these control points. And you can move these points around, and it'll manipulate the curve towards those points. So you can basically guide this, you can basically sculpt these curves into however you want. Here's one with more control points, and you can see that this higher order, these are higher order curves. And as a general rule of thumb for Bezier curves, you take the number of control points and you subtract one, and that's the order that you have, because that's the number of the layers of interpolations you have. So you have P0, P1, P2, P3. That's 4 control points. So this is a third degree polynomial. And again, you can see that nice interpolation. Add another one, you get an even higher degree. And you can see that once you start adding more control points, since the degree is a lot higher, you can see that it almost seems like the control points are affecting it less and less. It more becomes an average of the control points. So, and you can really see that in this case right here, this very bottom one. You have 1, 2, 3, 4, 5, 6 control points as a fifth order curve, and you kind of see that it just kind of averages out between them and then goes. And you know, a lot of times, depending on your application, you don't want that. You want it to be able to go towards that, and then down, and down, and up and down. And that's the downfall of Bezier curves, and that's where something called b-splines come in. Oh, one more thing that I want to say. You don't actually have to go constantly deriving those basis functions. The basis functions are always going to be the same for whatever order Bezier curve you want to do. You can literally just look these up in a table or something. You don't have to derive them, because deriving it from for a curve like this with 4 whatever layers of interpolations, that's not going to be a fun problem. So yeah, you can just look these up. Like for a, what order would this be? This would be a 1, 2, 3, 4. For this fourth order Bezier curve, I can look them up in the table. I can get my B0, my B1, B2, and my B3. and then I can just take whatever control points I want and multiply them by them, weight the basis functions by it, and then sum them all up, and I get my curve. So that's another cool thing about working directly with these basis functions. And again, the last thing that I want to reiterate is that in this formula, whenever you form the curve, don't forget that your points may have more than two coordinates or whatever. You might have an x coordinate and a y coordinate, or z or whatever, times your b naught plus your x coordinate of that one, p1y times that, and then again p2 x coordinate, p2 y coordinate times b2. So yeah, don't forget that you're not plotting this in parametric space. Like, you're not going to plot t comma the summation, the curve, and no, that's plotting in parametric space. No, we don't want to do that. We want to plot in physical space. So really what you do is, what you really get is, the C is a parametric description. Remember, it's really equal to an x of t and then a y of t, where these basis functions really multiply both parts of this. So just to be clear, for clarity and completeness, I'll write that out for you. So you get an x of t, y of t, and it's going to equal the x coordinate p naught x times b naught, and then p naught y times b naught, and then you add all the other ones. So p1 x b1 plus p2 x b2, and so on and so on. P naught y times b1 plus p2 y times b2. Yeah, so you get the idea. Just don't forget to plot it in physical space. You'd really be plotting, that, where that's that and that is that, the curve. So hopefully this is a decent overview of splines or Bezier curves. We still have b-splines, and then NURBS, and then t-splines, all which are used in analysis, isogeometric analysis, graphic design, creating fonts and computer graphics and all that. So really cool stuff, and thanks for watching.